Cool. Okay, so today I'll be looking at also center configurations. I'm sure you have received the handout that was emailed to you yesterday. So uh basically walk through that. So I think there's only three people here. So it'd be great if I could get some response for my questions if I ask any.
Okay.
All right, cool. So the author center is the intersection of the three attitudes of a triangle, of any triangle. So you see here the screen um, so this is altitude, the B altitude and the C altitude. They're all in the second point. And we call this for the author center. So the first exercise would be to prove the existence of the author center as illustrated on the handout. So has anybody tried to do that? Right. Let me just pull the handout real quick on my screen. Yep, so there are two ways to prove um why three how three lines are concurrent. So here we'll ask to just prove that AD is right actually. ADBE these um three lines are concurrent. So there are two ways you can do it. The first one would be use angle chasing. Angle chasing or length chasing with reverse construction. The second way would be use in this case Chambers theorem. So we look at the second wave first. So the first wave, we have to prove that um, B over DC, bar shape is illustrated on the header, times C over EA times AF over FB is equals to 1. So we have to compute this. And to do that, we could simply use the fact that BD is AB. So let's denote AB as C, AC as B, and BC as A. BD is C sine angle B. So in this triangle, BC is B sine angle C. The cosine, I should say. Cosine angle B. B's cosine angle C in the other triangle. C will be a cosine C. So it should sort of slip down C cosine A. That would be AE C cosine A times AF, that would be cosine A and A cosine B. And you see all of these, they cancel out. So cosine B, cosine B, C, cosine C. They cancel A, and this equals to 1. And by Chapel's theorem, we proved that AD, B, and CF are concurrent. Any questions? Or well, move on, I guess. So the next thing ties very closely to the um, Orthic center configuration. So we're trying to prove this using um, angle chasing with reverse reconstruction. And what I mean by so reverse reconstruction is a common technique in geometry, synthetic geometry. So I'm going to draw a new diagram. So ABC, and the condition I will use. So suppose E is a point on AC such that this is perpendicular, and suppose F is a point such that C is perpendicular to AB. So BU to AC and AB perpendicular to FC. So suppose um, this is true, but I want to prove that there's no reaction diagram. I want to prove that AD is perpendicular to BC. And if I can establish that, I prove that these three lines are current. So to do that, we have to make use of the fact that our conditions are that it makes you to make use of the fact that F, E, B, C are cyclic. And so let this point be H dash and A, F, H dash E are cyclic as well. So let's connect this line. So we basically just have to prove that B at H dash D is cyclic because this will show that H dash DC is 90 degrees, which is what we want. Right. Cool. So rest is a pretty simple angle tracer. So FEBC cyclic will tell us angle FBD is equals to angle AEF, and then AF H dash E cyclic just tells us angle AEF equals to angle AH dash F. So we have angle FBD equals angle AH dash F. So in essence, this angle is equals to this angle equals to this angle. And if you see in this quadrilateral, it will mean that these 4 points are cyclic. So FH dash DB will be cyclic. In fact, these are all equivalent. So angle FH dash A will be equals to sorry, angle AFH dash will be equals to angle H dash DB equals to angle ADB equals to 90 degrees. And we're done because we proved that it is from the cookies. So these are the two ways you can prove that the existence of the oval center. So I'll take a moment to digest it. And do you have any questions in the chat? Well, we can move on. So that's the existence of the auto center. And now we're going to look at the associated configurations. So the first thing that's the orthic triangle. Copy this diagram. So it's very useful to know when there's a bunch of 90-degree angles. It will create a lot of cyclic quadrilaterals as well as similarities. So the definition of the orthic triangle, so I'm trying to read this diagram. So the orthic triangle is the triangle formed by these three foot with the DF, this triangle. DF will be the orthic triangle. And this is very useful, in fact, because we'll have a lot of pairs of um, similar triangles as well as cyclic quadrilaterals, to name a few. There would be so FHDB cyclic, AFHD cyclic. So let's see, this is cyclic, and so you mentioned that FBBC is also cyclic. So that would be this bit. And so there should be 6 pairs, and you can try to find all of them. And there will also be a lot of similar pairs of similar triangles because of these cyclic quadrilaterals. So you know, if we have any cyclic quadrilaterals, so in any cyclic quadrilateral, um, these two triangles will be similar. So they're the ones which are vertically opposite. So this and this, these will be similar. And from there, you could find that. So and let's just say FECB. In this FEPC, and then you'll have triangle FHB, similar to triangle HEC. Cyclic just makes those 4 points lie on a line, so lie on the circle. So if we have a circle, and if we have 4 points on them, so, so we have ABCD, and then they all lie on the circle and called ABCD cyclic. So it's good to know some properties about circular quadrilaterals because it's very important in geometry. But I won't go into too much in this lecture. So yeah, to name a few, FEBC is cyclic, and we have FHB similar to HEC, or triangle FHE is similar to triangle BHC. Again, if you just take these out, so let's say FEBC. These triangles are also similar. So FEH and HBC. These are also similar. So try finding there should be 12 pairs of sort of triangle for one member. So try finding them all. You'll realize they're very useful. One last thing on the similar triangles. So if you extend so let's take the quadrilateral cycle quadrilateral FHBD and the triangle ABD. So it's ABD, H. So again, you will have triangle AFH similar to triangle ABD. So it's very good to use this, keep this in mind. In the future lecture, we'll talk about like tracing and PowerPoint, and these will come in really handy. So cool. I'll take a moment to digest this. All right. So once we establish these, it'll be very good to revise them after this, just to get to know the authors a bit better, being able to sort of use these properties in a very well, right? Okay, we're going to look at the important part of today, which is the lemmas. Uh, so I'm going to draw. So you see in the header, so I need to ortho triangle things that opposite can be. Could you elaborate on that? I suppose you mean uh, yes, in a cyclic quadrilateral, yes, in any of the cyclic quadrilaterals in the configurations, and then they are opposite, like FEH and HBC, they are directly opposite to each other. Um, they would be similar. Yeah, good question. So yeah, okay. In the header, you see there's a big diagram. Uh, looks pretty messy. Looks pretty complicated, but uh, once you get to know the lemmas, it should be easier to sort of visualize. Okay, so the first one we're going to prove is BHC is 180 minus BAC. We'll draw a diagram really quickly. So for a geometrical problem, whether the problem has stated the second cycle or not, it's always a good idea to draw a second cycle. In this case, we do need the circumcycle. So ABC, and then for sake of just really pinpoint this O, this H, and last proof, and then short draw. So this should be H, We were asked to prove BHC is 100 degree minus BAC minus. Okay, so this is not the hardest thing I want to prove. We can simply just take angle BHC, it would be angle BAC plus angle ABH plus angle ACH. This is not too hard to see, I suppose. This plus this angle will be that, and then this plus this uh, angle will be this one. So if you sum them up, we have BHC. And BAC is just BAC, so it's not anything too interesting. But ABH is a 90 minus BAC. So here you see this 90 degrees in BH. So BA, this angle and this angle, they are complementary. And the theory for ACH would be also be 90 minus BAC. So the BAC's cancel out and you have 180 minus BAC. This is a very useful and important property. That be the first lemma. And the second lemma is proof that BAH is equals to OAC. So let's connect this line. So important idea in geometry is reduction. You reduce the diagram into the elementary points. So if you see how this diagram is constructed, so you first have the three main points A, B, C, and then you get all of the orthocenter and the circumcenter. So what I mean by reduction is we want to prove that BAH equals to OAC. So this H is not elementary. In the sense, H is here. I want to go back to ABC. So a good thing to do is to reduce this to a like 90s. So to illustrate the point, with 90s minus BAH minus ABC. So you see how all three of these points, they are the sort of the elementary points, you would say. So did you see? This is BH is 90 minus BAC. These are complementary because of 90-degree angle. Shouldn't be too hard to see. And then OAC will be a bit more complicated. So I suppose you would know the the angle at the circle at the center is twice the angle at the arc. So let's just draw this is so suppose there's a point M and then OS particularly AC. Then we will have so to reduce OAC, so we could put M here as well. So to reduce OAC, it's simply 90s minus AON. And since AOC is half a center, so we have so AOC is since angle AOC equals to 2 angle ABC, and we know that angle AON is equals to angle MOC because the triangles AON and COM are congruent, which is also not too hard to see. So we have angle OAC is 90 minus angle AOC with 2, which is angle ABC. Like 90 minus angle ABC. So you see we reduce this to the most elementary form right here. And then we see these two things are equal once you reduce them to the sort of most basic expression you say. And we're done. So that's the first two lemmas. For the third lemma, I'll actually copy the starter. These right. I'll draw a new one actually. So for the third lemma, it's closely related to the orthic center. It's a direct result of the orthic center actually. So you have triangle ABC with the orthocenter H. You're asked to prove that the incenter. So if you don't know what the incenter is, it is the intersection of the three angle bisectors of the triangle, and they intersect the point, and it's called the incenter. I'll talk more about the incenter and its lemmas associated in the next lecture. So essentially, we have just to prove that um, AF bisects AF bisects angle DFE, and then well, labeled points wrongly. That's fine. CD bisects. Actually, no, really on points. DEF, and this triangle. So in essence, I have to prove that AD bisects angle FDE, FC bisects angle DFE, and BE bisects angle EFD. So that's the essence of it. And then this is pretty easy to see as well. You simply just notice angle, so FHDB cyclic. That would give angle FDH equals to angle HBF. And then DHEC cyclic. That gives angle HD. Angle HD is equal to angle HC. So you have, and you also know that FEBC cyclic gives angle FBE equals to angle FC. So you have angle FD equals to angle, sorry, FDH. FDH equals to angle EDH. And so we proved that AD bisects FE. And then similarly, you could say these two things are true because the diagram is symmetrical. So if you simply rotate this triangle so that C is on top, you could see that CF bisects EFD. and we're done. So this illustrates the power of the pairs of cyclic quadrilaterals in the configuration. So yeah, take a moment to digest them. All right. So the next one also pretty nice result. So next result is actually gonna be used for the recent ISM, but then it got put down for whatever reasons. So nice. We used to start like I'll show you. So you have triangle ABC. And if extend beyond that one, so this is H. Let's call this H dash. Oh, I call it X. I mean, hang on. So this call is point X. So H for this is a reflection of X. So that means let's call this point B. So HD will be equals to XD. Okay, this will be perpendicular. Now I also prove that ABX is cyclic. And it's also not too difficult. So um, if you have no idea how to tackle this, so let's say this was on the ISML, and you have no idea how you approach this because you probably haven't studied geometry enough. There's a really logical way to do this. So we're asked to prove ABXC is cyclic. So there are a lot of ways to prove that the quadrature is cyclic, and this includes angle tracing, length tracing, there's a lot of other terms they could use. So you play around. The idea with Olympian mathematics and problem solving is you play around with the problem statement. So ABXC is cyclic, we know that's true, and this will be equivalent to proving angle BAC plus angle BXC equals to 180. So this is equivalent to angle BXC equals to 180 minus angle BAC. And this thing should look familiar to you. So 100 this appear here, which is BHC. So it will be equivalent to proving angle BXC equals to angle BHC. And we know this is true because triangle BHC is actually congruent to BXC. So you see H is the reflection over BC. And that just directly makes these triangles all congruent. And we're done. So this is the one way you could sort of approach problem solving. If you have no idea how to tackle a problem, you play around with problem statement. And geometry is uh, is very useful. Well, next lemma. Okay, so we're going to work with this diagram as well. So we extend CH to a point here. Extend that would be Z. And we have to prove that these two arcs are equal. So just let me quickly look for the yep. So again, if you have no idea, so these questions are get a bit so harder, and they're not really levels to just useful results within three different spots. And again, if you have no idea how to tackle them, you can again use the idea of logical, like play around with the problem statement essentially. So bx arc bx equals to arc bx equals to arc bz. This is again equivalent. So you also need a good amount of knowledge of geometry to see if you can what you can do with the problem. This is actually equivalent to angle BAX equals to angle BCZ. So to illustrate, so BX it directly points to this angle BX, and then BZ would point to ZCB because of the arc in the circle. And we know that this is true because of the fact that triangle is to know this point. So that this would be F actually. So we know this because this is true because F A C and it extend so E here. Actually no, doesn't matter. So we know that this is true because F A C D is cyclic. So again, if we rotate the diagram and put D on top, it would basically be the same as BF is a cyclic. So this should be true. We're done. So another useful property. And then similarly, if you have so if extending y here, you have cx equals to cy, and you have az equals to and in fact h since h is in the center of h is in the center of triangle DEF, and since uh, DEF is similar to XYZ, because well, if you it's a homotopy at center H, we're talking about homotopy in a further lecture of factor 2. You have H is the center of XYZ. And this will get important if you learn complex fraction. It will give you a really useful way of denoting the ortho center and the center of the triangle. But if you don't plan on studying complex fraction, you ignore what I just said. Cool. So we're halfway there. The next one is a property that I'm really fond of, and it's also it's quite important. So we can recycle this diagram actually. Let's put two back. Right, this should be fine. So we extend HO. So we erase all these. Fold it. So we extend AO to a point A dash. So A dash would be the antipode. It'll be called the antipode of A with respect to the second cycle. So this would be O, and which asks to prove BHCA dash is a canonical. So again, since there are a lot of 90-degree angles, it's extremely easy to uh, generate uh, parallel lines as well, other than this aforementioned side quadrilateral semi-triangles. So that would be F. This would be D, E, F. So since AA dash is the diameter, these two angles would be 9 degrees. Angle AE equals angle AC dash, which is 9 degrees. Because the center is like Taylor's theorem, AC dash is 9 degrees. So we'll have BH is parallel to A dash C. So that's our first um, pair of parallel arcs. And similarly, since the diagram is symmetrical, so we extend here and X, and then we get the point F. Then we will have, so we have another pair of 9 degrees, so this is 9 degrees because AA dash is diameter. This is 9 degrees because it is 9 degrees by the definition of center. So A dash BA equals to angle CFA equals 9 degrees. So we will have CF parallel to A dash B. So that's what I meant when I was talking about uh, the incenter. So why are they sort of you just say similarly? Because the diagram is symmetrical, is sort of one. You could just basically write the same proof but with the different points. And you're done. And yeah, nice result. Uh, 7 with that. You can work with some diagram. So this combines with the previous lemma. So I draw, extend hx and then dx a dash c will be, and isosceles trapezium. Again, it is not too hard to see. So I'm going to be using, when there's an interpole, uh, so A dash is interpole because A dash is diameter. So whenever there's an interpole pair like this, you have a lot more than 90 degrees, and it would be very useful to consider them. And in certain problems, constructing the antipode will give you 90 degrees, which gives you a lot of conditions that you can work with, such as the 2023 IMO problem 2. So you want to look at that. So antipode. So you want to look at the 2023 IMO problem 2. It's a very nice way of using antipode to solve the problem. But that's besides the point. So yep, 7. So A dash should be 90 degrees. Would DADC also be 90 degrees? since this is true, we'd have BC prior to XA dash. Excuse me. Anyways, so we have BC prior to XA dash, and so we proved the first part. We proved that BX A dash C is a trapezium. So we proved one part, and we proved that it is isosceles. So this is quite a um, useful thing to remember. If you have a trapezium, which is cyclic, so in this case, x a dash c b, and we have a trapezium that is cyclic. I mean the trapezium that's from being cyclic, it is an isosceles trapezium because you can see these two. I'll do strictly so bx a dash plus angle xvc is 180, and then angle xa dash c plus angle xv0 is 180. This is because of parallel lines, because of the first one of parallel lines. Second one is because of cyclical quadrilaterals, and you can easily get angle xvc equals to angle a dash c. Right? Well, bxa dash equals to angle xh dash c, and then we're done. So yeah, try to improve the next exercise with your own 4-bit. It's very similar to this one. So I'll give you a few minutes. Yes, so the next trick is very similar, and in fact, it uses the stuff that we've used before. So we're asked to prove z, yeah. So we extend z and connect this. We're asked to prove that this is a isosceles trapezium. So C A dash B Z is isosceles trapezium, and we can simply just say that arc. So we proved that before. Arc bx equals to arc bz. So therefore, bz equals to bx. And this is again basic geometry in high school shouldn't be too surprising. And then we also know that uh, from the lemma 7 that bx equals to a dash c. So we would have bx equals to, because we have bz equals to a dash c. And again, we're done. So you could, yeah. So just see why this is true. Again, we look at this diagram. If these two sides are equal, if these two sides are equal, yeah, try this simple bit. Yeah, if these two sides are equal, then you get a pair of Gorman triangles in them. So that should be fine. Alright, let's move to the important lemma. Not importantly, something more elegant. So, in essence, all of these stuff that I've put on here is trying to prove this fact, which is so trying to prove this all the way. So let's copy this diagram. It's getting a bit messy, I know. Once you get better geometry, you know how to cope with these. So I actually don't need these, so basically. So, yes, so let's suppose you're on NZMO round 2, problem 3, you have to prove that AAC is equal to 2R cosine BAC. How would you approach it? So yeah, in essence, 9 is basically a guide to how to do 10. So I'll just put 9 10 here. So you're asked to prove on a random exam, on a perhaps the most important exam of life, you have to prove that AAC is equal to 2R cosine BAC. So again, let's try to let's try to play around with stuff we're dealing with and try to see where we can lead us to. So cosine BAC and the QR, these are really weird conditions. They don't seem to line up together. But if you look at our diagram, and based on what you know, what we just proved, and what you know about um, the orthosymmetric configurations, you immediately think of, oh, if I extend A dash, AL to A dash, then I'll get a trapezium, and I'll get triangles, and that'll be very nice. And most importantly, 2R is actually equals to A dash. So that's good to know. And that's a good thing to think about. Unfortunately, in this case, doesn't help us as much. So what I'm going to do is so we have a length condition, angle condition. So we either transform everything to a angle or everything to a length. So yeah, so in this case, we will angle to length. So I have R cosine, if you R cosine BAC. So I've also settled. So why don't I try let's BO? So you have these ideas and you try to play around with them. And you find out BO is equals to R. And cosine BAC, if you drop M, the midpoint, you BOM is actually equal to BAC. So again, when we talk about uh, this lemma, when we talk about the center of the circle and how that works. So BOM angle BOM is equals to angle BAC. So this will tell us R times 2R cosine BAC would actually be 2BO cosine BOM. And then BO cosine BOM will simply be BM. Oh, no, it would be OM, yeah. It would be OM. So right now we have to prove that AH equals to 2N. So nice. We've simplified the formula to something that's much simpler. And now this is where the lemma plays in that we've just proved of the parallelogram. So if we connect this, oh, it's really well drawn, isn't it? Turn that's a straight line. Man. So since M is the midpoint of BC, HMA dash would actually be collinear. Since M is midpoint of BC, HMA dash collinear. Because we proved that BHCH dash M is a parallelogram, and the diagonals they bisect each other. So if you look closely, if you look closely um, at these two triangles, so you notice that angle AH. So you notice AH is perpendicular to since AH is perpendicular to BC, and then OM is perpendicular to BC, we'll have AH is parallel to OM. And this basically means triangle A dash MO is similar to triangle A dash HA. So it's not also not too hard to see. Yeah, it's good in geometry diagram to draw a subdiagram out. So in this case, if you don't know why, it's A dash AH OM. If these two are parallel, then it's a homotopy of size. It's a homotopy. And we have some, and this case is very convenient for us because we know that HM is equals to MA dash because parallelogram diagonals bisect each other. So since AM equals to MA dash, it's in fact a homotopy of size too. So we have AH equals to 2M is required. And then this, of course, will be equals to 2R cosine of BAC. And we're done. In fact, if you want to use this on an obtuse triangle, in general, we have the absolute value of angle A. So for all triangles, and we are done with on the lemmas. So on the handout Just quickly, yeah, I'm close this point. So on the handout, you see there are a bunch of questions I've put in. So yeah, have a try those. They should be useful. Yeah, some of them are from the different contests, some of them from IMO, uh, some of them whatever. So have a go at them, and yeah, I'll see you in a month. Thanks for coming. So yeah, by the way, any questions or just or anything related to math or anything?